Okay, so today let's talk about the finite element method to solve the elastic problem. And today we will focus on the discussion of one typical element type called a constant strain triangle element, CST. So, okay, let's get started. Now, I hope you can all see this slide. Now, on the right-hand side, this is a solid material, elastic material. To solve the stress and strain in this solid material, typical way in the elastic class that you learned is to firstly find out the displacement field in this material, assuming this is in a 2D case. So you have only 2 degrees of freedom, 2 dimensions around the x direction and y direction. Now, your displacement field within this solid material is u as a function of x, y, and v as a function of x and y. U is displacement around the x directions, and at a different point, different x and y, they have different u. V is the displacement around the y direction, and it also is a function of x, y, the coordinate. Okay, and the u and v, they are perpendicular to each other. One is around x, one is around y, so they are decoupled. The magnitude or the effect of u will not affect the magnitude of v and the direction of the v, okay? Now, once we have u and v, the displacement field in this solid material, we can calculate the strain field in this solid material. To calculate it, we will have 3 strains because this is a 2D case. We have the sigma, we have the epsilon xx. Sigma is the stress, epsilon is the strain. Epsilon xx, which is the strain, normal strain around the x direction, which is the partial u, partial x. We also have the epsilon yy, which is the strain, normal strain around the y direction, equals to the partial v, partial x, partial y. We also have the shear strain, epsilon xy, okay? So once we calculate this 3 strain field, all of them are the function of coordinates. We can combine that with the constitutive relation or material behavior of this solid to calculate the sigma, the stress field. Here we write the stress field, the stress tensor equals to C tensor times epsilon tensor. So C is the material stiffness matrix. So the matrix of the stress equals to the matrix of stiffness times matrix of the strain. Here, remember in your elastic class, what you learned is a stress tensor. This is stress tensor, or we call it a stress matrix. It has 9 components. It has 3 normal stress and then 3 shear stress. Because later on in the class, we will show you the full matrix in the next few slides. Because this is a 2D case, we don't consider z direction. So the sigma zy, sigma zx, and sigma zz are all equal to 0. And also for the epsilon, the epsilon that is related to the z direction all equal to 0. So it's 2D case. The C tensor, stiffness tensor or stiffening matrix also contains 9 components. It contains the Young's modulus and the Poisson ratio. Strain tensor also has 9 components. So in the elasticity method, what you do is to find out the continuous displacement field u and v in this solid elastic object, and then do the differentiations to get the strain field. and then combined with the elastic properties or the constitutive relationship, which is this equation shown here, to obtain the stress field. Then you will get the full mechanical properties of the solid material. That's called elasticity approach. What we will discuss today is a finite element approach. This is a little bit different. The advantage of using finite element analysis approach is, for the elastic material, if you want to use this method, elasticity approach, to solve their complete mechanical solutions, this material, the geometry, the shape has to be well defined. Such as the cylinder, perfect cylinder, or perfect square shaped material, so that their analytical solution are easy to obtain, they are available. But in the practical experiments or in the real world, the geometry of the object you are going to analyze, they will have a different shape, right? And also the material may have different properties at a different region. They may not be continuous or the homogeneous material. They could be heterogeneous material. So in this case, finite element approach actually provide a numeric avenue for us to obtain the complete mechanical solution of the object. So that is why the finite element method is so powerful. But we need to keep in mind, finite element method actually is a simulation method. It's not an analytical method as the elastic approach does. Elastic approaches. So depending on how you analyze, how you choose the element type to analyze those objects, the results could be dramatically different. So you need to know the theory of finite element, which we will discuss today. And also we need to analyze these problems appropriately so that you can get the approach, you can get your results more accurate or closer to the real analytical solution. Okay. So today let's talk about one type of most fundamental finite element. So first, let's step back. What kind of elements are available in the finite element analysis? So there are many kinds of elements available, such as there are triangle elements, like this shape, triangle elements. Those elements, this one you see that is linear. They have 3 points. In the finite element, we call it 3 nodes, and then 3 edges, right? You can see my mouse, 3 edges. They are linear. And it can be more sophisticated, and you can add the nodes into the edge of the triangle. So you can have a quadratic triangle elements. You can not only add 1 node to each edge, you can add 2, such as the cubic. It becomes cubic triangle elements. You can also add the nodes in the center of the triangle elements. All it does is add those nodes to help you to more closely or more accurately simulate or approach to the numerical solution. Okay, we will discuss those gradually. You can also choose the elements with different geometry. In addition to triangle elements, we can also choose regular angle elements, such as here. You have the linear regular elements, and you can also add increase the number of the nodes to make it the regular angular elements become quadratic regular angular elements or cubic, or you can also customize it, make it become mixed regular angular elements. Depends on the problems you are going to solve. The reason why we change those nodes in all those elements is because in the finite element, all the solutions actually existing in the nodes. So the element are actually, element actually contain all the information, stress, strain, and the displacement all on the nodes. And then for the point not on the nodes, like on those edge or in the center, we do the fitting, we do the interpolation to get approximate results. So the condition on the nodes are the first most important data we need to use. Okay, by increasing those node number, we can make the result. We can use higher order polynomial equations to simulate the stress, strain, and the displacement, and make the result to be more precise. And I have talked about the quadratic and the cubic elements in both geometry, both geometry elements now. So now let's talk about, let's see if we put those elements on this material, what will happen? So for the object, when we mesh it, mesh means we separate those material into small elements, into small discrete portions. Each portion, like this portion, is an element, and they have the nodes at the side, and then connected with another element. For this geometry, and solids, we will put bigger element or the element with coarse size in the center, because in the center, the material, the geometry is more simple. But put the more dense elements or smaller elements, more elements at the edge, at the boundary. Because at the edge and at the boundary of this object, the geometry, the shape is more irregular. So you want to use more elements to cover all of them correctly, okay? And more elements added at those irregular surface can make the results more, can add more value into the node, make the results more close to the real solution. In the future example, in the future, we will have also a hole in the solid material. And then if you have a hole in the center, you need to make a very fine mesh around the hole, and then gradually increase the size of the element when you move away from the hole. So as you know, if you took the fracture mechanics or the material of mechanics class before, you know that if there's a defect in the material, you will have the stress concentration. So the coarse element around a defect or around the hole cannot represent the real stress field. It will miss many detailed information. So we need to make the mesh very dense around the defects to capture the authentic stress and strain field. Okay, we will talk about it in details in the future slides. Now, as I said, yeah, mesh on this 2D solid, we have a small element at the boundary because this guy has no hole. It's a bulk material, and they have the irregular shaped boundaries. So we need to add more smaller elements to densely mesh to cover the edge, so that the results are more accurate. Okay, and those will lead to the closer solution to the exact results, exact solution. One thing very important is when you look at those elements, though they are actually connected at the nodes. So all the nodes, there are no free nodes that are connected with nothing. Every node is connected with every node is connected to many different elements. And those elements share both node and edge, right? So like this element and this element, they share one edge and two nodes, this one and this one. But only this nodes contains the information, contains the displacement information. And the elements communicate with each other through the nodes, not through this edge. Later on, you will see our examples showing that for these two elements, the displacement results are common on this point, on these 2 points, okay? And the stress and the strain in each element could be actually different. Also, in this case, in this 2D case, each element has for the triangle elements, each of these triangle 2D elements, they have 3 nodes. Each node has 2 degrees of freedom around the x direction, around the y direction, and the displacement is u and v on each node. Okay, so if we look at one element, it will be look like this. You have a node 1, node 2, node 3. Here, we assign the index of node to each element. So that's why we have the node 1, 2, and 3. It doesn't matter which node is node 1. But in this case, in this right-hand coordinate system, so x this direction, y this direction, so this is a right-hand coordinate system. If you put your right hand here and rotate your fingers, you will rotate from x to y, right? So that's counterclockwise. In this kind of counterclockwise coordinate system, once you define a node as node 1, then the node 2 and the node 3 all follow counterclockwise direct rotating. Okay, node 1, node 2, node 3. If you make this one node 1, then this is node 2, this is node 3. Okay. On each node, you will have, as we said, you have 2 degrees of freedom. You will have displacement u1 on the node 1, u2 on v1 in the y direction. For node 2, we will have u2 around x direction, v2 around y direction. For node 3, we have u3 around x direction, v3 around y direction. Here, x1, y1, x2, y2, and x3, y3 are the coordinates of each points. And here we are actually sitting in the global coordinate system. So x1, y1, basically xi and yi, they are all the coordinates of these 3 points. And on each point, they have corresponding displacement ui and vi. So in the finite element, you will firstly solve the displacement on each node. So you will have the u1, v1 on the node 1, u2, v2 on node 2, u3, v3 on node 3. You will not have a continuous uxy on the whole element. You only have discrete data point. From there, we will try to solve we will try to approximately get the map of the displacement, continuous displacement field. Okay, that's through the interpolation. We will talk about it. We will talk about this in detail. We will derive it. So that's the fundamental difference between finite element approach, which is a discrete approach, with respect to the elasticity approach, which is a continuous approach. Okay, so both methods has advantages and disadvantages. Finite element method is very general. Any material, any geometry, you can discretize it, and then by solving the node solution, and then you further do the interpolation to get a continuous solution throughout the body of the material. elasticity approach, you can get the continuous solution rather quickly, but they are all only limited to the well-defined geometry, well-defined shaped object, and the material properties has to be relatively straightforward, relatively simple. For very complicated material property combinations, it's very hard to get a simple analytical solution. You can still use the series method to solve it, but it's more complicated and not very easy to use by the people. Okay. Okay. Now, today let's talk about a fundamental finite element type, which is called a CST. CST stands for constant strain triangle. You can also call it a constant stress triangle. It's also CST, and they are actually, as you will see, they are that definition is also correct. Now, here is one example of one CST element. You have 3 nodes, 1, 2, 3 in the counterclockwise sequence. Now, we have talked about this. For each point, you have each node, not each point, they have 2 degrees of freedom, 2 displacements. We will also have 2 forces on this displacement, because the force will lead to this displacement. They are called Fxi, Fyi for different nodes. There are no force or no displacement on the edge. Those mechanical parameters only defined on the nodes, not on the edge. Okay, and then later on we will find out that the stress and the strain within this whole CST element actually are constant. So the whole thing has a constant stress and strain. And if you have many of those elements connected together, shared the edge, and shared the nodes, but they are tied together, you will find that if the stress and strain are different, they will have different color in the finite element software. If you plot them in the contour map, they have different colors. Means they have each element contain one single stress or single strain. Okay, so that's actually also the reason if you want, you can make the finite element size smaller, make it a more dense mesh. You will have a smooth transition of the stress instead of a jump or step change of the stress and strain. Okay. Okay. So our goal now is to get the continuous displacement distribution within this CST element, given the displacement values in the 3 nodes of the element. So in this case, we will use the polynomial equations to simulate the displacement field in this element. When we write the to be solved displacement field uxy, so this is to be solved, we write it as in the terms of the polynomial equations. They will have we can write it as alpha 1 plus alpha 2x plus alpha 3y plus alpha 4x squared plus alpha 5y squared, or plus alpha 6xy. You can go on, right, until the xn, yn. Now, when we write then in terms of the polynomial equations, we want to solve those alpha 1, alpha 2, alpha 3, those constants based on the displacement u1, v1, u2, v2, u3, v3. Of course, here is we talk about the u displacement, so we only use u, u1, u2, u3. we will not use V1, V2, V3 because they are perpendicular to each other. As I said, they are decoupled. Now, if we have those polynomial equation and we have the constant here, we have actually only 3 no values, U1, U2, and U3. So then we can only solve 3 unknowns. So we can only solve alpha 1, alpha 2, and alpha 3. We cannot solve alpha 4, right? You can only get a relationship, but that's not exactly solved. So in this case, the polynomial equation we choose will be alpha 1 plus alpha 2x plus alpha 3y. In that case, this is a linear equation, okay? And let's look at this equation carefully. If, imagine, we solved this equation, we have the uxy solved here. That is an equation existing in this element. They have a constant term and a x linear term and y linear term. What does that mean? That means it has this displacement around the x direction, u displacement. They actually have a term that is not dependent on x and not dependent on y. This is a constantly moving term. That is called a rigid body motion. So the whole element is moving. Once this element is moving, every point has the same displacement around the u. If you have the x term here, means as the coordinate x increase, the displacement also increase. So there is a shape change, okay? Same thing for the y term, y linear term. If the y increase around the y direction, y coordinate increase, the u displacement also increase. So that means there's a shear term there, okay? Okay, so for the v is the same thing. You can have the vxy equals to alpha beta 1 plus beta 2x plus beta 3y. And we also don't have the fourth and the higher order term. We only have 3 terms to solve these 3 unknowns based on the 3 no displacement values given. Now, our goal is to find out this uxy, this displacement distribution, okay? To find out this, this alpha terms actually doesn't mean anything. What we really interested in and what we really have in hand actually is the given displacement u1, u2, u3. So we would like to express alpha terms in terms of the u, okay? So we want to get the displacement field map in terms of given displacement u1, u2, u3 on the node, okay? How to do that? Now, here, actually, I already explained those things. Yeah, this is the x u continuous u displacement field right in the alpha 1, alpha 2, alpha 3, and they are all they are a function of linear x, y, and v also as a beta 1, beta 2, beta 3, and the linear term x and y. Here, alpha 1, beta 1 are the rigid body motion around the x direction and the y direction, okay? So let's focus on the u first. Focus on the u displacement map first. As I said, we want to convert those alpha terms, alpha constant terms, into the given displacement values. Once we put the displacement value u1, u2, u3, their combination into those alpha terms, then we can choose any x, any y, and find out the corresponding u displacement within that element. So eventually we will have a function looks like this. Uxy equals to n1, which n1, u1, n2, u2, n3, u3. This actually is don't worry about how we derive it. we will derive it for you in the next few minutes. But what I have rearranged this equation. Okay, so you have x and y. Their x, y are variable. They change, and you put u1, u2, u3 into those constants. Then you arrange it to sort out u1, sort out u2 and u3, and they are associated with the x, y functions. Okay, and then you put the x, y coordinates you want into this function, and you can calculate the displacement of that point with the coordinate x and y. Okay. Now let's together derive this equation. So firstly, look, we know we are using the polynomial equation to simulate to simulate the displacement. Now, if we stand on the point 1 or the node 1, you have a coordinate system on this node 1 as x1 and y1. You have displacement u1. Okay, same thing happened to the node 2, point 2, and node 3. Okay, then you will get 3 equations. You have u1 equals to alpha 1 plus alpha 2 x1 as a coordinate point in the node 1, and then alpha 3 y1, that's the y coordinates of this point. Okay, you have this equation. Same thing for the node 2 and node 3. You have u2 equals to alpha 1 plus alpha 2 x2, alpha 3 y2. And then for the node 3, you have u3 equals to alpha 1 plus alpha 2 x3 plus alpha 3 y3. Remember, all those three equations actually coming from this one equation. Okay, you put the node 1, it's the coordinates and the displacement into this equation. You get this first equation. You put the node 2 information into this equation, node 3 information into this equation. You get a second, third equations. Okay, so you have 3 equations, and you input all the nodes, and you have 3 unknowns: alpha 1, alpha 2, alpha 3. Now these 3 equations, this equation set, can be written also in terms of matrix notation. You will put them, we can put them as a 1 by 3 matrix, u1, u2, u3 in the bracket. Okay, this is the 1 by 3 vectors. This equals to 3 by 3 matrix times 1 by 3 matrix, alpha 1, alpha 2, f3. Okay, so this one is a 3 by 3 matrix. This is a 3 by 1 matrix. So 3 by 3 times 3 by 1 give you 3 by 1 matrix at the results, which matches with this, right? So our goal is to solve you use this, you can solve the alpha 1, alpha 2, and alpha 3. Of course, written in this form, you can also, once you know alpha 1, alpha 2, alpha 3, you can put that into this form to solve any point you are interested within this element, any random point. Okay. By the way, do you remember what is this? This matrix is a 3 by 3 matrix. What is this? Let's look at this. It is written as x 1, 1, 1, and x1, x2, x3, y1, y2, y3, right? So this matrix, what does this mean? If you remember, let's let me go to the board. If you remember, so my question is, for this 1, 1, 1, x1, x2, x3, y1, y2, y3, for this matrix, if you calculate this, if you can calculate the determinant of this, my question is, what is this? What it is remember, in the if you have two vectors, okay, start at origin, you have x1, y1, x2, y2. Okay? You have this kind. If you do the cross product, this is the vector A, vector B. Remember, if you do the cross product, A vector times B vector, that will give you the area of this. If you take the magnitude, this of course it will give you a new vector. This is a new vector by the right-hand coordinates. Okay. This if we have another vector here, which is 0, 0, 1. Okay. Then it's called a C vectors. If you have this guy, dot products with C, you will get a volume. Okay. But what I'm saying is this A and B, if you cross product it, you get, because you will get the area. C, the magnitude equals 1. So this value eventually equals to the magnitude is equals to the area. Now, think about this. What does this mean? This actually is the same thing. This is the displacement. This together will equals to this. If this is the element, node 1, node 2, node 3. This determinant actually gives you, if you have a vector here, this guy will give you the area of the whole thing. Okay? And the determinant of this equals to 2 times of the area of this element, of this CST element. Okay? Let me go back. Okay, so this is the element. The coordinate, the determinant of this matrix actually equals to 2 times the area of this triangle. Now, second thing important for this matrix is these points, x1, x2, x3, these 3 points, if they are not collapse or overlap with each other, all these 3 points are not aligned in one straight line, then they will form a triangle, 1, 2, 3. Then this matrix is not a singular matrix, means the determinant of it is not 0. And as I said, determinant equals to this the area, half area, no, double area of this triangle, right? So if the determinant of this guy is not 0, then it's not a singular matrix. If it's not a singular matrix, this can be inversed. Okay, we are going to inverse it because we want to find out the alpha 1, alpha 2, alpha 3 based on those no factors. Okay. Okay. Now, as we once we inverse that matrix, we will have you can calculate it by the linear algebra skills. You can calculate it. If you have question about how to calculate it, let me know. I can show you the detailed derivation. But here I will just give you the results. The inverse of this matrix actually equals to 1 over 2a. A is the area. Okay, 2a is exactly the determinant of the matrix of this matrix. And then another matrix, 3 by 3 matrix, F1, F2, F3, B1, B2, B3, C1, C2, 3 times the U vectors. Here, F, B, C, they are actually the function of coordinates. So for example, F1 equals to X2, Y3 minus X3, Y2. And same thing for the F2, you need to carefully check the index, but they are all in similar forms. Same thing for the B is equals to Y2 minus Y3, B2, B3, and C is equals to C1 equals to X3 minus X2, and you can calculate C2, C3. Those things actually putting together, the dimension-wise is also correct. So they can be put to the inside, and then you can calculate what's the final matrix looks like, and then this 3x3 matrix times the 3x1 vectors will give you another 3x1 vectors corresponding to the alpha 1, alpha 2, alpha 3. Okay, and here, as I said, the determinants of this matrix equals to double of the area of this CST element. Okay, now once we write it in the form, once we write the alpha vectors, alpha 1, alpha 2, alpha 3 in terms of the x1, x and y coordinates and u displacement, then we can actually we can sort this algebra. We can find out this should be the alpha. I don't know why in the PowerPoint they changed the alpha to A. We will correct those things and upload the slides in the Canvas, so you can use the correct form. But this actually is alpha 1. So this alpha 1 equals to 1 over 2A F1 U1 plus F2 U2 plus F3 U3. Okay, same thing, you can calculate alpha 2 and calculate alpha 3. When we get those alpha 1, alpha 2, alpha 3, we can put them back to the U function. Okay, so U function continuous U displacement function equals to alpha 1 plus alpha 2x plus alpha 3y, right? So we put them here and then result it. You have the U inside, U1, U2, U3 inside, extract the U1, extract U2, extract U3, then you have the X functions inside. So you can write, and each term in front of the individual U, individual X direction displacement, we can write it as the N function. So N bigger, N1, XY stand for the combination terms in here, in this box, okay? Same thing for the N2. N2 equals to all the terms involved that are associated with U2. N3 is all the terms associated with U3. So eventually you can write this one as, what I want to see is you write as a U, N1, U1 plus N2, U2 plus N3, U3. And that can be written, that equation can be written in the matrix form. Is equal to, the U will be equal to a 1 by 3 matrix N1, N2, N3 times a 3 by 1 matrix vector U1, U2, U3. Okay. Same thing for the V. It's actually interesting thing is that those number actually is the same. For the V, in the Y direction equals to N1, N2, N3 times V, V1, V2, V3. Okay, and the expression of the N are written here. Okay, this actually equals the N3. We will correct this. These are very important function. These three, N1, N2, N3, they are actually called a shape function. So this is a very famous function in the finite element. And for the CST element, constant stress or strain triangle element, their shape function are in this form. They are all linear, X and Y, right? And at constant term. Depending on what kind of element you use, the shape function will change. And basically those shape function will determine how you fit the curve, how you do the interpolation to get the results get the results not on the node, but in the element. Okay. In the CST element, N1, N2, N3 are the linear functions, and they can be calculated using the nodal coordinates. So you put the x1, x2, x2, x3 into this into those nodal function. You will get exactly displacement u1 and v1 on the x1 on the node 1, and correspondingly you can get that in the node 2 and node 3. Okay, that's exact results. But for the node outside of these 3 nodes, they are fitted by this node function, shape functions. So we can, based on those functions, we can do the linear interpretation to get the displacement. Okay. Okay. Those functions, as I said, they are all linear, right? So how do you think about those things? How do you think about those? Why this linear? Why those linear functions can be used to interpret the point not on the node? Why? This is actually pretty simple. We have 2 examples here to help you understand this problem better. Now, imagine, firstly, you have a roof. Okay, the roof is flat. Roof is flat, but it is tilted. It has some angles with respect to the horizontal. On the roof, since it's flat, if you point out 3 points or 3 nodes on the roof, then you know the height of each points, h1, h2, and h3. You connect these 3 points to form a triangle. Then any points on the node, any point on the element, either on the edge or in the center, you can actually find out their height, their edge, right? Because this is the roof is flat. This triangle-shaped element is actually correct. Give you the correct solution. Once this triangle overlaps on the top of the roof, you can get every point correctly. As long as you know the coordinate system, coordinate of any point, you can get the edge on that spot. Another example is the temperature, the weather. So the temperature here, this is a US map. If you wanted to know the temperature on any point, given the temperature, 3 temperature points in Texas, Illinois, and Texas in Florida, pick up 3 cities, you know the temperature. And then you want to know what's the temperature in other cities within this triangle. You can also do the similar things to get an approximate value of the temperature there, as long as you know the coordinates of that point. But you obviously you can see that here use a triangle may not be very exact, because the temperature variable is not a linear variable, right? They actually have a very complicated functions built in. So use the triangle element is not appropriate. It's very approximate. It's actually a very approximate way to find out any point, the temperature of any city within this triangle, right? But this explains the concepts. You can do the fitting, do the interpretation to find out the point within the triangle elements. Okay. Okay. We will continue in the next lecture about the more detailed information about this CST element.